Welcome back to Programming Fluency. This is section 11.2, Memory Checking with Valgrind. Your program passes every test and then, hours later, the server runs out of memory. In this video, you will learn a tool that finds memory bugs you cannot see. Let's begin. Your program runs without crashing. It produces correct output. Every test passes. You ship it. 3 hours later, the server runs out of memory because your program was leaking a little memory on every single request. These are invisible bugs. They do not crash until it is too late. In this video, you will learn Valgrind, a tool that finds memory bugs you cannot see. Let's get started. This is the plan for this video. First, invisible memory bugs. Leaks and corruption that never crash until it is too late. Next, the mental model. Valgrind is an X-ray machine that checks every memory access. Then finding a leak. You run Valgrind -- leak check equals full and read the leak summary. After that, reading errors. Invalid reads, use after free and uninitialized values. Finally, the workflow. Compile, run, fix one error, and rerun until it is clean. GDB pauses your program and lets you inspect it, but GDB catches crashes and logic errors. It does not catch silent memory corruption. Look at two examples. A program leaks 64 bytes on every request. It runs fine today, but after 100,000 requests, it runs out of memory. Or a program reads from a free buffer. Most of the time, the old data is still there, so the output looks correct, until a different allocation reuses that memory and the program silently returns the wrong data. These are invisible bugs. No crash, no warning, just wrong answers later. To catch them, you need a tool that watches every single memory access your program makes. So what is Valgrind? Valgrind is a dynamic analysis tool. It runs your program inside a virtual environment, and it monitors every memory access. Its default tool is called Memcheck. Memcheck detects memory leaks, invalid reads and writes, use after free errors, double freeze, and reads of uninitialized memory. And for every error, it reports the exact source line and the call stack, just like GDB's backtrace, but for memory errors that never crash. Think of Valgrind as an X-ray machine for memory. It wraps your program and intercepts every memory operation, every read, every write, every allocation, and every free. This figure shows the loop. For every byte, Valgrind tracks three things. Is it allocated or freed? Is it initialized or not? Is the access in bounds or out of bounds? If any check fails, Valgrind reports it and keeps going, then prints a leak summary at the end. The trade-off is speed. Valgrind makes your program run 10 to 50 times slower, which is fine for debugging but not for production. This is a program with a deliberate memory leak. The function makeArray allocates memory with malloc, fills it, and returns the pointer. Main calls it, prints the first element, and returns, but look at the comment. There is no free of data. The memory that makeArray allocated is never released. This is a memory leak. The program runs fine and produces correct output, so nothing looks wrong. Let's run it under Valgrind and watch Valgrind catch the leak. First compile with -g-big O0, exactly like for GDB, then run Valgrind, -- leak check equals full, then your program. Read the output. The heap summary says 20 bytes in one block were still in use at exit. That is 5 ints, 4 bytes each. Then Valgrind says 20 bytes are definitely lost, and it shows the stack trace. So -- leak check equals full reports every leaked allocation. Read the stack trace from the bottom to the top. Main, on line 14, called makeArray, on line 5, which called malloc. So the 20-byte allocation on line 5 was never freed. The fix is one line. Add free of data before the return. The leak summary sorts leaks into 4 categories. First, definitely lost means no pointer to this memory exists anywhere. It is unreachable. Always fix this. It is a real leak. Second, indirectly lost means a pointer to the memory exists, but only from a block that is itself lost. Fix the root leak, and this resolves automatically. Third, possibly lost means a pointer to the interior of the block exists, but not to its start. Investigate it. Fourth, still reachable means a pointer to the memory still exists at exit. This is usually not a bug because the operating system reclaims all memory at exit. The takeaway: focus on definitely lost first. Those are your confirmed leaks. Valgrind also catches out-of-bounds access. Here a program allocated a 5-element array and read array index 5, one past the last valid index. On most systems this does not crash. It silently reads whatever is in memory just past the block, but Valgrind catches it. It says, invalid read of size 4, which is one int, at bounds.c line 14. Then the crucial detail. Address is 0 bytes after a block of size 20. Since the array is 5 times 4, or 20 bytes, index 5 lands exactly one element past the end. Valgrind gives you the size of the access, the source line, and the nearest allocation. The fix is to change array index 5 to array index 4. Let's look at a program with 3 bugs at once. Bug 1. It allocates counts with malloc, then reads counts index 0, 1, and 2 and adds them without ever assigning values first. That is reading uninitialized memory. Bug 2. It allocates name, copies Alice into it, frees name, and then tries to print name. That is a use after free. Bug 3. The counts allocation is never freed, a memory leak. Let's see how Valgrind reports all 3 in a single run. This is Valgrind's output and it catches all 3 bugs. First, use of uninitialized value at triple.c line 11. That is bug 1. Second, invalid read of size 1 inside a block that was freed at line 18. That is bug 2, the use after free. Third, 12 bytes definitely lost. That is bug 3, the leak. For the uninitialized value, use calloc, which zeros the memory, or initialize each element. For the use after free, move the print before the free. Setting the pointer to null after freeing does not fix it, because the later print would then pass a null pointer to %s for the definitely lost block. Add the missing free. Fix them one at a time, and rerun Valgrind after each fix, because one bug can hide or cause another. After all these examples, the workflow is clear. It is 5 simple steps. Step 1. Compile with -g-big O0. Debug symbols and no optimization, exactly like GDB. Step 2. Run Valgrind with --leakcheck equals full, and exercise all your program's normal inputs in code paths. Step 3. Read each error report. Every error has a type, a source line, and a stack trace. Step 4. Fix one error at a time. Start with the first error reported, because later errors may just be consequences of the first. Step 5. Rerun Valgrind after every single fix. The target is 0 errors and 0 leaks. Do not ship until you see all heap blocks were freed and 0 errors. 2 common mistakes. First, thinking still reachable means leaked. If Valgrind says still reachable, 1024 bytes, you might think you have a leak. but still reachable means a pointer to that memory still exists at exit. This is common for global buffers and library internals. The operating system reclaims it anyway, so it is usually not a bug. Focus on definitely lost and indirectly lost, which are the real leaks. Second, running Valgrind on an optimized binary. If you compile with -big O2, the optimizer may eliminate reads and writes that Valgrind needs to see, so it misses errors or reports them at confusing locations. Always use -g-big O0 under Valgrind, and save -big O2 for release builds you have already validated. Let's recap. GDB finds crashes and logic errors. Valgrind finds the other kind, invisible memory errors that silently corrupt data and leak resources. Together they form the professional C programmer's debugging toolkit. Run Valgrind with -- leak check equals full to detect leaks and memory errors. Read each report for the error type, the source line, and the stack trace. Valgrind finds memory leaks, invalid reads and writes, use after free errors, and uninitialized values. Interpret the leak categories, and remember that definitely lost always needs a fix. And follow the loop. Compile with -g-big O0, run, fix one error and rerun until clean. Next, GDB catches crashes and Valgrind catches memory errors, but many C bugs fall into recognizable patterns. In the next section, you will build a pattern library so you can diagnose most bugs on site.